We'll close this class by talking through a handful of advanced topics related to the course material. In this course, we've already discussed a variety of goals, methods, and paradigms of knowledge-based AI. Now let's close by talking through some of the advanced applications of this content. We'll also talk quite a bit about some of the connections with both AI and human cognition. Many of the topics we'll discuss today are very broad and discussion-oriented. So we encourage you to carry on the conversation on the forums and discuss some of the issues that this content raises. Visual-spatial reasoning is reasoning with visual-spatial knowledge. This has two parts to it, visual and spatial. Visual deals with the what part, spatial deals with the where part. So imagine a picture in which there is a sun on the top right of the picture. There are two parts to it, sun, the what, the object, and where, the top right of the picture. We have come across visual-spatial reasoning a little bit when we use constraint propagation to do line labeling in 2D images. One way of defining visual-spatial knowledge is to say that in visual-spatial knowledge, causality is at most implicit. Imagine a picture in which there is a cup with a pool of water around it. You don't know where the pool of water came from, but you and I can quickly infer that the cup must have contained the water, and the water must have spilled out as the cup fell. So in visual-spatial knowledge, causality is implicit, but it enables inferences about causality.
There are several ways of how we can deal with visual-spatial knowledge. In fact, in your projects, you've already come across some of them. So imagine there is a figure here. Here is a triangle with the apex facing to the right. Here is another triangle with the apex facing to the left. So in one view, the AI agent can extract propositional representations out of figures like this. And similarly, propositional representations out of figure like this. So this is a propositional representation, this is a propositional representation. And then the AI agent can work on these propositional representations to produce new propositional representations. So some AI agent can use a logic engine or a production rule to say that this particular triangle, which was rotated 90 degrees, has now been rotated to 270 degrees. So although the input was in the form of these figures, the action here was at the level of propositional representations of these figures. The AI agent may extract propositional representations like this through image processing, through image segmentation, perhaps using some techniques like constraint propagation as well. Alternatively, the AI agent may have analogical representations. In these analogical representations, there is a structural correspondence between the representation and the external figure. So the external world had a triangle like this, and the analogical representation will also have a triangle like this. Notice that I'm using the term analogical representation, which is a separate thing from analogical reasoning. We are not talking about analogical reasoning right now. We're talking about analogical representation. And analogical representation is one which has some structural correspondence with the external world that is being represented. Given such an analogical representation, then I might run affine transformations or set transformations to get this. So I may say that I got this triangle out of that one simply by the operation of reflection or rotation. So these propositional representations in the previous view are amodal. They are separated from, divorced from the perceptual modality. These analogical representations, on the other hand, are modal representations. They are very close to the perceptual modality. In human cognition, mental imagery appears to use analogical representations. What would be an equivalent theory of computational imagery? Human cognition is very good at using both propositional representations and analogical representations. Computers, however, are not yet good at using analogical representations. Most computers, most of the time, use only propositional representations. The same kind of analysis may apply to other perceptual modalities, not just to visual images. So here are two measures, and we can either extract propositional representations out of them and then analyze those propositional representations, or we could think directly about the relationship between these two particular measures. Here is a question for building theories of human cognition. When you're driving a car and you listen to a melody on your radio, and you're reminded of something, reminded of a similar melody that you had heard earlier, what exactly is happening? Are you extracting a propositional representation out of the melody that you just heard? And then the propositional representation reminds you of the propositional representation for a previously heard melody? Or does the new melody somehow directly remind you of a previously heard melody without any intermediate propositional representation? These are all open issues in cognitive science as well as in knowledge-based AI. In cognitive science, there is by now significant agreement that human cognition does use mental imagery, at least with visual images, but we don't know how to do mental imagery in computers. This chart summarizes some of the discussion so far. Content deals with the content of knowledge, and coding deals with the representation of knowledge, content and form. The content of knowledge could be visual-spatial, that deals with what and where. Where is spatial, what is visual. And the encoding for visual-spatial knowledge could be either analogical or propositional. An analogical encoding of visual-spatial knowledge, there is a structural correspondence between the encoding and the external world that is being represented. In the propositional representation of visual-spatial knowledge, there is no such correspondence. Examples of this verbal knowledge include things like scripts for going to a restaurant. The script for going to a restaurant, again, can be represented either propositionally or potentially analogically. In a propositional representation of the kind we saw, we may have tracks and props and actors. An analogical representation of the script for going to a restaurant, we may have a short movie. In much of the course, we have dealt with the right-hand side of this chart, with verbal knowledge and propositional representations. Part of the point of this lesson on visual-spatial knowledge and reasoning is that reasoning and knowledge can be visual-spatial and the representations can be analogical. But we have yet to fully understand their role in human cognition, and we have certainly yet to build AI agents that can deal with visual-spatial knowledge and analogical representations. One AI system that does do visual-spatial reasoning is called Galatea. It was developed by Jim Davies here at Georgia Tech about 10 years back, which is why it looks black and white and has this particular form. We provide a reference to the paper in the notes. There is a very famous problem in analogical reasoning called the Dunker radiation problem. The Dunker radiation problem goes something like this. First, I'll tell you a story, and then I'll give you a problem, and you have to try to find an answer to the problem. Let me begin with the story. Once there was a king, and not a especially good king, who ruled a kingdom. There was a rebel army that was trying to overthrow the king, but the king lived in a fortress, and it was very hard to overthrow him. Moreover, the king had mined the roads so that when the army went over the roads, that mine would blow off and most of the soldiers in the army would die. The leader of the army decomposed the army into smaller groups, and these smaller groups then came to the fortress from different directions. Because each group was small enough, the mines did not blow off, and each group was able to reach the fortress at the same time. There then, they were able to overthrow the bad king. So this was the story. Now let me tell you about the problem. There is a patient with a cancer tumor in his body. There is a physician with a laser gun. She can use the laser gun on this tumor to kill this tumor and cure the patient. However, the laser light is so strong that it will also kill all the healthy tissue in the way and the patient may die. What should the physician do? In most computer models of this problem is solved using propositional representations. So an example of a propositional representation for the original story might be that if there is a goal and there is a resource and there is an obstacle between the resource and the goal, then split the resource into many different smaller resources and bring them to the goal all at the same time but from different directions. Most computational models of the Dunker radiation problem extract some causal pattern. The causal pattern might be that if there is a goal and there is a resource available and the resource can achieve the goal, but there is an obstacle in the way, then decompose the resource into many smaller resources and bring them to the goal in the same time from different directions. The important part here is that this is the causal pattern extracted out of the first story. Once this causal pattern has been abstracted, it can be applied to this new problem. So the physician may decompose the laser beam into lots of smaller beams and put all of them to the tumor at the same time, thus curing the tumor. Jim wanted to ask whether one could do the same kind of problem solving without extracting these causal patterns. Could one use simply visuospatial knowledge? So this is visuospatial knowledge because there is both a sense of what, the fortress, as well as where in the middle of the figure. Notice this visuospatial knowledge is represented propositionally. There are words like here like fortress and right road and top road and so on. But there is no causality that is explicit. You and I can infer the causality, but it's not explicit. His Galatea program was able to find a solution to the new problem by transferring this visual-spatial knowledge to the new problem one step at a time. Thus, it would map this top body part to the top road one here, the left body part to the left road here, and therefore decide that this can be decomposed, this resource, denoted by this arrow, can be decomposed into smaller resources. And then the smaller resources can arrive at the central tumor from different directions at the same time. In this way, Galatea was able to solve the Dunker radiation problem without abstracting any causal pattern from it. Of course, one might say that the causal pattern is implicit here, and that is indeed true. But the entire point about visual-spatial knowledge here is that the causal pattern is not being abstracted, but as long as it is a problem-solving procedure where each step is being represented only visual-spatially, it is possible to transfer the problem-solving procedure to the new problem. We just saw an example where visual-spatial knowledge by itself suffices to do analogical reasoning under certain conditions. Now let us look at a different problem. There certainly are situations where we might want AI agents to be able to extract propositional representations. Your projects 1, 2, and 3 did exactly that. One task where an AI agent might want to build propositional representations out of visual-spatial knowledge is when an AI agent is given a design drawing. So here is a vector graphics drawing of a simple engineering system. Perhaps some of you can recognize what is happening here. This is the cylinder and this is the piston. This is the rod of the piston moves left and right. The other end of the rod is connected to a crankshaft. As this piston moves left and right, this particular crankshaft starts moving anti-clockwise. This device translates linear motion into rotational motion. I just gave you a causal account. Although causality was only implicit in this visual-spatial knowledge, you and I were able to extract a causal account out of this. How did we do it? How can we help AI agents do it? At present, if you were to make a CAD drawing using any CAD tool that you want, the machine does not understand the drawing. But can machines of tomorrow understand drawings by automatically building these causal models out of them? Put another way, there is a story that is being captured in this particular diagram. Can a machine automatically extract that story from this diagram? In 2007, Patrick Yanner built an AI program called Architas. Architas was able to extract causal models out of vector graphics drawings of the kind that I just showed you. This figure is coming from a paper in Architas and hence the form of the figure. We'll have a pointer to the paper in the notes. This is how Architas worked. It began with a library of source drawings. These were drawings that it already knew about. For each drawing that it already knew about, it already had done this segmentation. These basic shapes, for example, might be things like circles, and the composite shapes, which were then labeled like piston and cylinder. Then a behavioral model or a causal model, which said what happens when the piston moves in and out, namely the crankshaft turns. And then a functional specification, which said that this particular system converts linear motion into rotational motion. So there was a lot of knowledge associated with each previous drawing that Architas already had seen. All of this knowledge was put into a library. When a new drawing was input into Architas, then it generated line segments and arcs and intersections from it. And then it started mapping them to the lines and segments and arcs of previously known drawings. Retrieved the drawing that was the closest matching drawing to the new drawing, and then started transferring basic shapes and then composite shapes, and it transferred each element through this abstraction hierarchy all the way up to the functional level. As an example, if Architas library contained piston and crankshaft drawings like this, along with causal functional models for them, then, given a new drawing of a piston and crankshaft device, Architas would then be able to assemble a causal functional model for the new drawing. Thus, Architas extracted causal information from visual-spatial representations through analogical reasoning. It may interest you to note that the projects you have been doing in this class are based on cutting-edge research. Until just a few years back, all computational models of solving problems on the Raven's test first extracted propositional representations from the figures and then ran propositional engines on those propositional representations. Thus, they may extract the transformation from A to B in the form of a semantic network shown here. And similarly, they may extract the transformation from C to 5 through the semantic network shown here. They would then compare these two semantic networks and decide whether or not A is to B is similar to C is to 5. You may have done something similar in your early projects. But in 2012, Maithili Kunda here at Georgia Tech was able to write a computer program that used only analogical representations without extracting any propositional representations, and yet were able to solve problems on the Raven's progressive matrices test. It used only affine and set transformations over the analogical representations. So as an example, it would compare A and B by saying that there is a set transformation, this particular dot is no longer there. And there is an affine transformation, in fact two affine transformations, first that make this square bigger, and second that translates the position of the square from inside the circle to outside the circle. It would find similar affine and set transformations that would relate C and 5. That will compare the affine and set transformations, again without extracting any propositional representations. Little surprisingly, Maithili Kunda's program called ASTI, for ASTI, was able to do quite well in the Raven's test. It solved 50 out of the 60 problems correctly. Then in 2013, Keith McGregor, again here at Georgia Tech, wrote another computer program that used a different kind of analogical representation called the fractal representation. And he was able to show that the fractal representation also enables addressing problems on the Raven's test with a good degree of accuracy. We provide references both Maithili's work and Keith's work in the notes.
In this class, we have talked a lot about how AI agents must be able to reason about the external world. But the external world consists of systems of many different kinds. A system is composed of heterogeneous, interacting components. The interaction between components lead to processes of different kinds. These processes can occur at many different levels of abstraction. Some of the processes might be invisible. Consider an ecosystem. In an ecosystem, processes occur at many levels of abstraction: physical, biological, chemical. Some of these processes are invisible to the naked eye, but they influence each other. Similarly, in business, businesses are composed of a large number of interacting units: manufacturing, marketing, delivery, and so on. Each of these units can be described at many levels of abstraction, from individuals to teams to full organizations. Given that the external world consists of systems of different kinds, AI agents must be capable of systems thinking. They must be capable of thinking about the invisible processes of systems, about the complex behaviors of systems. In particular, they must be able to derive the invisible processes from the visible structure. This is systems thinking.
We can connect systems thinking to several topics we have already covered in this class. You may recall that early on in this course, we used frames to understand stories of this kind. Now, this story is actually capturing some information about a system. In this particular system, there is a country with people and president. It also has geological faults, as a result of which earthquakes occur that kill some people. So the components, the complex relationships between these components, and the complex processes that emerge out of those interactions between the components. Scripts, too, are related to systems thinking. Dining at a restaurant is a complex system. Once again, there are a number of components, relationships, interactions, processes, functions. And script is a knowledge representation that allows us to capture knowledge of a stereotypical dining experience at a restaurant. When we discussed diagnosis, at that time we talked about systems thinking a little bit more explicitly. To begin with, we said that diagnosis is identification of a fault responsible for a malfunctioning system. Diagnosis begins with the observed data about some system violates our expectations of the behavior expected of it. The diagnostic task takes the data and maps it into a hypothesis about faults responsible for that behavior. What makes the diagnostic task so hard, again, is that there are a large number of components that interact with each other, and there's a complex behavior that emerges out of the interaction between those components. Just think of program debugging. Program debugging is hard because there are a large number of lines in the code, and these lines in the code interact with each other, and very complex behaviors, output behaviors, emerge because of those interactions.
So another good example of how diagnosis is a case of systems thinking is if we look at ecological systems. Recently, there's been a massive drop in the population of bees around the world. That's our data. Now, as it turns out, the cause for this drop in bee population is the presence of a poisonous substance in insecticides used in the past several years. However, we can't see the process of bees getting poisoned by this chemical. All we can do is infer it based on higher level interactions of seeing the bee populations drop and seeing a rise in this chemical. So in this way, there's multiple levels of abstraction in this process. There's the visible bee population, there's the visible use of pesticide, but there's also an invisible layer where the pesticide actually poisons the bees. So we have to discern the interaction between these multiple levels.
In any complex system, there will be many levels of abstraction, some invisible, some visible. The human eye or human sensors more generally can see only some of these levels of abstraction, the visible levels of abstraction. Systems thinking helps us understand the invisible levels. So AI has developed representations that help capture both the visible levels of abstraction, structure for example, and the invisible levels like behavior and function. Therefore, these models are sometimes called structure, behavior, function. Let's take a simple example. All of us are familiar with the household flashlight. You press on the button and light comes out of the bulb. What you can see is the button and the bulb and the body of the flashlight. You can even open the body of the flashlight and you might see some batteries inside the flashlight. That's all you can see. But of course, there is more going on here. To begin with, this particular flashlight has a function. This function is invisible. You can ascribe to it, but it's nowhere inside the body of the bulb. One level at which it is useful to analyze the flashlight is to ask ourselves, what does it do? Not yet, how does it work? Just what does it do? Its function. Here is a representation of the function. Here is the function create light of that light bulb circuit or the flashlight light bulb circuit. There is some stimulus, some external force on the switch. Initially there was no light, 0 lumens, and finally there is some light, 30 lumens. This captures the notion that when I press on the switch, light comes out. Here is a representation of the structure of the flashlight. Here is the light bulb, the switch, and the battery. And they are connected. All of them are attached. Here is the invisible causal process that we are calling behavior. We'll capture this behavior through a series of states and transitions between these states. So here is electricity, initially in the battery. Then this electricity flows from the battery to the bulb. And then the bulb converts this electricity into light. But in order for this electricity to flow through the bulb, this particular switch has to be in the mode on. The switch goes into the mode on when someone presses on it. Electricity is converted into light because that's the function of the bulb. Notice that these SBF models are nested. We just gave an SBF model of the flashlight circuit. But now if you want, we can get to the SBF model of the light bulb itself. How does it create light? In this way, structure, behavior, function models capture not just the visible structure, but also the invisible causal processes, the behaviors, and the functions. Moreover, they capture that at multiple levels of abstraction, at the level of the flashlight, at the level of the bulb, and so on. We will not describe it in detail here, but structure, behavior, function models and other similar models enable systems thinking in the context of diagnosis and design of complex systems. We have provided some readings about this in the course materials if you want to read more about it.
When we talked about configuration, we alluded to design. Design is a very wide-ranging, open-ended activity. But then we settled on to configuration, very routine kind of design, where all the parts of the design are already known. We simply have to figure out the configuration of the parts. It is time now to return to design thinking. What is design thinking? Design thinking is thinking about ill-defined, under-constrained, open-ended problems. Let's design a house that is sustainable is an example of design thinking. Sustainability here is ill-defined. The problem is open-ended. In design thinking, it is not just that the solution that evolves, it is that the problem evolves as well. We have problem-solution co-evolution.
As we have mentioned earlier, configuration is a kind of design, a kind of routine design. And one method for doing configuration is plan refinement. In configuration, all the components of the design are already known, but we have to find some arrangement for the components, and we assign values to some of the variables of those components to arrive at an arrangement. Here is a design specification that one begins with. Here it might be a plan for designing a chair as a whole. And once we assign values to some of the variables at the level of the chair, then we can refine the plan for the chair into a plan for the chair legs, the chair seat, and so on. All of this might be subject to certain constraints. There are in fact a number of AI systems that do configuration design. Many of them are being used in industry. Some of these AI systems use methods like planned refinement, the way we have shown it here. Others use case-based reasoning. In fact, AI systems use a variety of methods for doing configuration design, including model-based reasoning and rule-based reasoning. What about more creative kinds of design? Design in which not all the parts are known in advance. Since we just discussed the flashlight example in the context of systems thinking, let us revisit that example in the context of creative design. So this is a schematic of the flashlight circuit. Here is the switch, the battery, the bulb as earlier. Under systems thinking, we discussed how structure behavior function models capture the knowledge that when the switch is closed, electricity flows from the battery to the bulb, and the bulb converts that electrical energy into light energy. Let us suppose that this particular electrical circuit used a 1.5 volt battery and created 10 lumens of light. Tomorrow someone comes to you and says, I want 20 lumens of light, design a flashlight electrical circuit for me. How will you do that? You might go to the structure behavior function model of this particular circuit and do systems thinking. You may recognize that the amount of light created in the bulb is directly proportional to the voltage of the battery. So instead of creating 10 lumens of light, you need 20 lumens of light. You might say, I'm going to use a 3 volt battery. So far, so good. You've done systems thinking in the context of design thinking. But now let us add a wrinkle. Suppose that a 3.0 volt battery is not available. At this point, a teacher tells you it's okay if a 3.0 volt battery is not available. You can connect two 1.0 volt batteries in series. Two 1.5 volt batteries connected in series will give you the voltage of 3 volts. Accepting the teacher's advice, you can now create an electrical circuit that will use two 1.4 volt batteries in series and create light of 20 lumens. But you not just created this particular design, you also learned something from it. Every time you create a design, every experience is an opportunity for learning. In the mid-1990s, Sam Bhatta here at Georgia Tech created a program called IDEAL. IDEAL did creative design. In particular, IDEAL would learn about design patterns from simple design cases of the kind we just talked about. I'm sure most of you are familiar with the notion of design pattern. Design patterns are a major construct in software engineering. But design patterns occur not just in software engineering, but in all kinds of design, for example, architecture and engineering and so on. Here is Sam's way of capturing the design pattern that can be learned from the previous case. If you know the design of a device that changes the value of some variable from one value to another value, and you want another design that changes the value of the same variable to some other value, not the same as the previous design, one way in which you can create the new design is by replicating the behavior of the previous design. So not just having behavior B1 for the first design, but having this behavior B1 as many times as needed. Let us connect this to the example we just saw. If you have a design of an electrical circuit that can create 10 lumens of light, and you know how to do it through some behavior B1, I need to design an electrical circuit that can create 20 lumens of light, but you don't know the behavior B2. Then, this behavior B2 is a replication of the behavior B1 by connecting components in series. Once Sam's program IDEAL had learned about this design pattern of cascading, of replication, then when it was given the problem of designing a water pump of higher capacity than the one available, it could create a new water pump by connecting several water pumps in series. Thus, IDEAL created new designs in one domain, the domain of water pump, through analogical transfer of design patterns learned in another domain, the domain of electrical circuits. Viewed from the perspective of the new domain of water pumps, initially did not know about all the components, about all the water pumps that will be needed. But Sam's program IDEAL was creative enough to know that the pattern of problems here in water pump is exactly the same pattern that was also occurring in the domain of electrical circuits. Sam's theory provides a computational account of not only how design patterns can be used, but also about how these design patterns can be learned and transferred to new domains. There is, of course, a lot more to design. We said earlier that design thinking engages problem-solution coevolution. It's not just that the solution evolves while the problem remains fixed, but that the problem evolves even as the solution evolves. It's not yet clear how humans do this kind of creative design where there is problem-solution coevolution. There certainly are few AI systems capable of problem-solution coevolution at present.
This brings us to the topic of creativity. We humans are naturally very creative. And I'm not talking just about an Einstein or a Mozart. You and I are very creative on an everyday basis. You and I constantly deal with novel problems. And when we deal with novel problems, we don't just give up. We address them, and most of the time fairly successfully. Now, the goal of knowledge-based AI is to create AI agents that can think and act like humans. So shouldn't we also create knowledge-based AI agents that are creative? But in order to answer this, we have to define what is creativity. Now, in lesson 1, we saw how hard it was to define intelligence. Defining creativity is no less hard, but we'll give it a try anyway.
In order to build AI agents that are creative, it might be useful to think about what is creativity. Please write down your answer in this box and also post your answer on the class forum. What do you think is creativity, David?
So after much deliberation, I decided that I would define creativity simply as anything that produces a non-obvious, desirable product. I think that we have to have some kind of output for creativity in order for it to actually be identifiable as creativity. I think that the output has to actually be wanted in some way. Doing something that no one wants is not necessarily creative. I think the output has to actually be desirable in some way, and it also has to be something non-obvious. Doing the obvious answer is not a very creative solution. If I'm propping open a door and I use a chair, that's a slightly more creative solution to that problem.
Thank you, David. Of course, everyone's answer to this question might differ. For example, some people may not put the word product here. It's not clear that the result of creativity is necessarily a product. Some people may not put the word desirable there because sometimes creativity may not result from some initial desire. Let us carry on this discussion of what is creativity on the forum. Feel free to add your own notions. In the computational creativity community, whose goal is to develop AI agents that are creative in their own right, the current definition of creativity is that something is creative if it is novel, valuable, and unexpected. Notice that this deals not just with creativity in the sense of design creativity, but with all kinds of creativity. So this could be a scientific discovery that is creative, novel, valuable, unexpected. This can also capture art or music. The notion of value there may not be a monetary value, it might be of some interest to a recipient. Creativity typically involves both a producer and a receiver. Notice that this notion of unexpectedness is connected to David's notion of non-obviousness.
So Ashok, what exactly is the difference between novelty and unexpectedness? If something's novel, isn't it also unexpected?
Good question, David. Novelty here deals with newness. Unexpectedness here deals with something non-obvious or surprising. Perhaps this will become clearer if I take an example. So imagine if we decide to entertain a group of 20 friends. We already know how to make soufflés according to a particular recipe. We'll make soufflé for 20 friends this time. We have never made soufflé for 20 people, so it certainly is novel, something new, something we haven't done earlier. On the other hand, we have known this recipe for ages. Something unexpected would be if we come up with a new recipe for the soufflé which tastes dramatically different, surprisingly different. Not just something new, but something unexpected. So far, we have been talking about the product of creativity, the result of creativity, the outcome of creativity. What about the processes of creativity? We've used the term here, some and other. Both of these terms are important. Let's first look at the term other. In this course, we already talked about several processes of creativity. Analogical reasoning is a fundamental process of creativity. We already explored analogical reasoning in the context of design. We just did that when we were talking about design thinking. One might be able to design a new kind of water pump by composing several water pumps in series if one can analogically transfer a design pattern from the domain of electrical circuits, was our example. Similarly, under analogical reasoning, we were talking about the processes that might be used to come up with a model of the atomic structure by analogy to the model of the solar system, which clearly is a creative process that cuts across large number of dimensions of space and time. Another place where we talked about creative processes was when we were talking about explanation-based learning. It seems creative if the robot can go to the kitchen and use the flower pot as a cup to bring you coffee. Here are three other processes of creativity: emergence, re-representation, and serendipity. A simple example of emergence is that if I draw 3 lines, 1, 2, 3, then a triangle emerges out of it. The triangleness doesn't belong to any single line. I was not even trying to draw a triangle. I just drew 3 lines and a triangle emerged out of it. The emergence of the triangle through the drawing of 3 lines is a kind of creativity. Re-representation occurs when the original representation of the problem is not conducive to problem solving. So we re-represent the problem and then commence problem solving. To see an example of this, let's go back to our atomic structure and solar system problem. Suppose that we have a model of the solar system which uses the word the planets revolve around the sun. We also have a model of the atom, and this uses the term the electron rotates around the nucleus. So the model of the sun has the word revolves, and the model of this atom has the word rotates. The two vocabularies are different. If you were to stay with these propositional representations, mapping between rotate and revolve will become very hard. On the other hand, suppose we were to re-represent this problem. We re-represent the atomic structure by drawing the nucleus in the middle and the electron around it. We represent the solar system by drawing the sun in the middle and the earth around it. Then, in this new representation, we can see the similarity, we can do the mapping. This re-representation is another fundamental process of creativity. Serendipity can be of many types and can occur in many different situations. One kind of serendipity occurs when I'm trying to address a problem but I'm unable to address it. So I suspend the goal and I start doing something different. Later, at some other time, I come across a solution and I connect it with the previous suspended goal. The story has it that in 1941 in France, Georges de Mistral's wife asked him to help her open a dress by pulling on a zipper because it was stuck. Mistral struggled with the zipper but couldn't pull it down. Later on one day, Mistral was walking his dog when he found that some birds were stuck to the dog's legs. Curious about this, Mistral looked at the birds closely under a microscope. He then connected the solution, the bird solution, to the opening of the zipper problem. And out of that was born the notion of Velcro, which you and I now use on a common basis. Now, just like the word other was important here, these are three processes. In addition to the processes we already discussed in this class, the word sum is also important here. This is not an exhaustive list. There are in fact additional things we can add. For example, another potential process here is called conceptual combination. Let us do an exercise together. Here are a number of tasks that we have come across in this class. For each of these tasks, mark the box if you think that the agent that performed that task well is a creative agent. What do you think, David?
So actually, I marked none of them. It seems to me that for all of these tasks, if an artificial agent that we design accomplishes the task, we're able to go back and look at its reasoning, look at its processing, and figure out exactly how it did it. So it's never going to be unexpected. It's always the output of a predictable algorithm.
Interesting thought, David. Not sure I agree with it. Let's discuss it further. Do you agree with David's assessment that none of these AI agents is creative because we can trace through the process that the agents used? Well, let's look at each of these choices one at a time. The first one says yes, because in order for a result to be creative, it must be novel. An output of an algorithm cannot be novel. Well, there are a few problems with this particular answer. While an output of an algorithm for a small, closed-world problem cannot be novel, the output of combinations of algorithms for open-ended problem can, and indeed sometimes is, novel. There are algorithms, for example, that do design or they do scientific discovery whose results are novel. Let's look at the second answer. Yes, because given a set of input, the output will always be the same. Therefore, the product can never be unexpected. The output will depend not just on the input and not only on the methods of the system, but also the situation in which the methods are situated. The output depends not just on the input and the method the AI agent uses, but also the context in which the AI agent is situated. For example, given the same input but different context for the input, the agent may come up with very different outputs, very different understandings of that same input, as we saw in this section on understanding. The third answer, no, because it defines creativity in terms of the output than the process. This answer too has problems, because sometimes creativity can be defined simply in terms of the output without knowing anything about the process. We can think of a black box that creates very interesting creative music. We may not know anything about the process it is using, but if the output is interesting in creative music, we would consider it to be creative. Personally, my sympathies lie with the fourth answer. But of course, you are welcome to disagree with me. Why don't we continue this discussion on the forum?
Finally, the last topic we'll cover in this class is AI ethics. Often, scientists go about doing science without asking questions about the ethics of the science they do. We are also engrossed in questions of funding and proposals and papers. However, part of our job as scientists is to ask the question about, are we doing the right kind of things? There are a large number of questions connected with the ethics of AI. We'll post a small number here today. There are no easy answers to these questions, so we invite you to discuss these questions on the forum. First, AI ethics pertain to our economy and our society. We have talked a lot in this course about designing AI agents that can act and think and behave like humans. However, in the process, we quite likely will replace some human jobs with robots. We have talked, for example, of robots that can assemble a camera. Does this mean that humans who assemble the cameras today will lose their jobs? Of course, a counter-argument is that new jobs might be created, for example, jobs for designing robots. Nevertheless, there are hard issues about the ethical implications of AI in terms of human economy and society. Second, much of the modern development of AI is driven by defense applications all across the world. We already have drones, for example. It is not far-fetched to imagine a future where there are robot soldiers on the battlefield. What are the implications of introducing robot soldiers? Should we build morality into these soldiers? How do we do so? And if we are to build morality into robots, what does it teach us about our own morality? A third and related question is that if we start building human characteristics like creativity and morality into AI agents, at what point do these agents become like humans? At what point do we start talking about civil rights for these machines because they are indistinguishable from humans? The idea has been touched upon in the popular culture a lot, but it is coming closer and closer to reality. What are the criteria under which we would consider machines to be equal to humans?
So today we've covered some of the most advanced and cutting-edge topics in knowledge-based AI. If anything we've talked about today has really caught your eye, we invite you to check out the course materials where we've provided several readings about each topic. As we said at the beginning, many of the things we've talked about today are open issues that the community is wrestling with right now, so we encourage you to take up the discussion over on the forums. We'll be there participating as well.
Please write down what all you learned in this lesson in this box.
Great. Thank you very much.